Okay, 10.3 is about the dot product, which hopefully you have seen before in other courses. Might need a refresher on it, or maybe you haven't seen it before. Basically, the dot product applies to vectors. So we might have vector A, which in component form is A1, A2, A3. So that would give you your X, Y, and Z. Okay, and we're going to be working in 3D a lot in Calc 3, so I'm going to throw that third dimension on there right away. It could just as easily be a two-dimensional vector, which only have an A1 and an A2. Okay, and then you might have vector B, which also has three components. Your X component, B1, your Y component, B2, and your Z component, B3. Okay, now your dot product would be, if we did A dot B. Okay, that's how it would be written. And your dot product would be A1 times B1. Getting all these colors here, but plus, and then we're going to do A2 times B2, and then A3 times B3. And so I don't have to switch back and forth. I'm just going to write A2, leave room for B2 in the plus, and A3. Okay. So that's what your dot product would be. In your dot product, we've got two vectors. Okay, and then your result is what we would call a scalar. So when you perform a dot product or calculate a dot product, it's a scalar. So I would encourage you to look at some of the examples in the book for that, because I don't want to make this video too long, and most of you have seen this before. Okay, I will point out there are some properties on the bottom of page 551. I would familiarize yourself with those. They do show a proof for two of those properties, and then say that the rest are in the homework. So one thing that you will find, especially at the beginning of the course here, is that when you have some of the quizzes and assessments, you are asked to prove certain properties. So get used to kind of decoding those, and definitely practice the ones that are in the homework. So I'll just show you a brief one here. They have you prove the property that a vector dot producted, I think that's a verb, dot producted with itself is the same as the magnitude. Remember those horizontal bars, vertical bars mean magnitude of vector A squared. Okay, so if I were going to do that, I would say vector A is A1, A2, A3. Then A dot A would be A1, times A1 plus A2 times A2 plus A3 times A3, okay, which is A1 squared plus A2 squared. Remember, when you're doing a proof, you try to stick to one side, okay, which is the square root of A1 squared plus A2 squared plus A3 squared squared. And so that is the magnitude of vector A squared. Okay, I think they show fewer steps in the book because that's kind of a straightforward one, but definitely look at the other ones. because those get a little bit more complicated. And again, you will have quizzes where you have to perform proofs like this. So make sure that you are kind of reviewing how to do those. Okay. The next thing that you have probably seen before also is this formula for angle between vectors. And you will see this rearranged and written in different ways. But the cosine of theta, or theta would be the angle between two vectors, is the dot product of the two vectors over the product of the magnitudes. Okay, so remember too that your dot product helps to kind of think about these things. Your dot product will be a scalar, and then each of these magnitudes are also scalars. Okay, so you will get a number that's a scalar, and that's the cosine of the angle between them, and then inverse cosine will give you the angle between them. Okay, this is also proven using the law of sines, or actually law of cosines, on page 552 in your book, if you want to take a look at the proof of that. That one gets a little bit more complicated, not super straightforward. Okay, but one thing to kind of notice there is, think about this question. What will have to be true if two vectors are orthogonal, which is kind of a fancy word for perpendicular. Okay, so what must be true if two vectors are orthogonal? Okay, in other words, the angle between them is 90 degrees. Okay, so if we look at that formula, okay, think about this. I'm going to put 90 degrees here. Okay, the cosine of 90 degrees is, think about, I'll give you a wait time there. Think about that for a second. What is the cosine of 90 degrees? Think about your unit circle. If I'm at 90 degrees, my x-coordinate is 0. So coordinate of 90 degrees, the cosine of 90 degrees is 0. Okay, so what that means then is that the dot product has to be 0. Okay, so that's an easy way to tell if two vectors are orthogonal, is if the dot product is 0. All right, one more concept with your dot products. And again, make sure you're looking in the book and following along with some of the examples in the book too. I don't want to put it all in the video because it gets too long. And you guys know how to read, so you can definitely do those on your own. Okay, we're going to talk about projection. Projection of vectors. Okay, so let's say that we have vector A, that's this direction. Let's say that this is vector A. Okay, and then let's say that we have vector B, and just to make this diagram easy, we'll have the same, we'll situate them so that their initial points are the same. Okay, so let's say that this is vector B. Okay, and then there's an angle between them of theta. What we would do is we could project B onto A, which is kind of, think about the component of B that's in the same direction as A. You can almost think about A as being like your x-axis. And if you tilt your head and look at the x-axis, you want the x component of B. Okay, but now it's not the x-axis, it's just some vector in space. So we want the component of B that's in that direction. So the projection of B onto A would basically be right here. Okay, so some people teach it as like, think about holding a flashlight that's perpendicular to A. Let me see if I can move this out of here quick, just a second. Okay. If I have my little flashlight, if you've had me before, you know that I like to draw, right? So if I have a flashlight, okay, and that flashlight is perpendicular to vector A, and it is shining. Okay, so think about where the shadow of B would be on A. Okay, isn't that fun? That's good. Okay, so that little pinkish reddish vector there, that's what we would say is the projection onto A of B. Okay, and then we also have something called the, let me get the right term here quick. Does your book call it? It's the orthogonal projection. I don't think they really talk about it much in your book. Okay, well, I'm going to put it out there anyway. So we can also think about then the other component that would be perpendicular to A. So we'll call that the orthogonal projection of the vector onto A, vector B onto A. Okay, so what you can see here too is, if you remember how vectors are added, the projection onto A of B plus that orthogonal guy will equal B. Okay, if you remember how you add vectors together, where the first one has terminal end is where the next one's initial end is, and then you connect the initial to the final terminal. Okay, so that's how vector addition works. All right. So we have a couple calculations that we can do here. So the first one is what we call the component in the A direction of B. Okay, and this is a scalar. Okay, basically it's the same thing as the magnitude of that projection. So we're going to break this up a little bit. Okay, we're not worried about the vector form of that guy yet, just the magnitude of it. Okay, and we can just use right triangle trigonometry to get that, right? It would be the magnitude of vector B times the cosine of theta. Okay, that's just how right triangles work, right? Okay, so I'm going to write that component of B on A is equal to that. And what we just learned is the cosine of theta is A dot B over the magnitude of A times the magnitude of B. So those magnitudes of B cancel out. So that's just A dot B over the magnitude of A. Okay, so that would give us the magnitude, again, of that projection. Okay, so then the next thing we need to do is to get the projection, which is a vector. Okay, so all we need to do is take that magnitude, okay, that we got in part 1 there, and multiply it by a unit vector in the direction of vector A, okay, to get the direction there. So we will do vector A divided by the magnitude of A. Okay, remember that is a unit vector in the direction of A. Okay, so it gives us our direction with a magnitude of 1, and then this one gives us the magnitude. Okay, so we put those together and we'll get our vector that we want. Okay, that can also be simplified here a little bit. You will see it written as A dot B, we don't combine, because this is a dot product, right? We can't separate that out. Like you can't make the A squared or anything like that, but you can square the magnitude. Okay. And then A. Okay. And then the last thing is your orthogonal projection of B. Okay, and we just get that by subtraction. That's going to be B minus your projection onto A of B. Okay, that just uses that formula right above it. Okay, so that should get you going on your homework for vectors. And in the next video, we're going to do cross products.